So really nice to have you. Quantum Mechanics 531. And let's see if it is recording as we expect. Are you recording? Yes, I can see the green go up. Yeah, it is recording. So I now can start my PowerPoint and we continue for today's slideshow. All right. Let's see if we can make the lighting a little bit better. Maybe dim it. Just things. That's what lecture 0 is. Checking that everyone is comfortable. So you tell me what works best for you. Is it better? Or you want it? Is it better now?
I feel like you can see it pretty easily.
Yeah, that's fine.
Sure. This is okay for seeing?
Yeah.
And then you can still write. All right. So what are your expectations about quantum theory? What does it do? Quantum mechanics. Are you taking it just because you have to? Hope not. Take it because it's so cool. See all that we can do with it and have already done with it. See the applications, evolution of the entire universe. It helps us there, especially relativistic quantum mechanics. Then look, bombs.
That's what I was laughing about.
Defense. Okay, who helps? Continue. Read. Next person.
Medical uses.
Example. Anybody? Quantum mechanics and medical uses?
Like radiation therapy?
Yeah, radiation therapy. Where does quantum mechanics work? Well, we now understand photons and what they can do. Yeah, so I didn't intend to continue using this while actually teaching, but while interacting, it may be something. Yeah. So, medical uses are so many. Who has ever done MRI? Very good. You benefited immensely. Magnetic resonance imaging. When we first gave it the name that fits the quantum theory on which it is based, namely nuclear magnetic resonance, patients were refusing to go there. They didn't want to do the imaging. Once nuclear, no, not me. Then we changed the name to magnetic resonance image. Yeah, people got it. But it is about nuclear spin. Something we will do in chapter 4 of our book. Yeah, chapter 4 and chapter 5. Spin, which is like, and our understanding of spin is quite limited. We're still struggling with it. In fact, we are using understanding of angular momentum to apply to spin, and it works. Yeah. So, materials and technology, atoms and molecules. Who are chemists? Who are chemistry majors? Physical chemistry. There's a lot of applications there. Then, who else? Read.
Quantum cryptography.
Oh yeah, you prefer that. I too, I like that.
Yes.
It's in the making. Yeah. So who has ever used a quantum computer? Not yet there, but there's a lot of work on it. Yeah. And this might help us overcome some issues with people taking us for granted, taking our data, stealing it, and then you have to pay money to get. So hacking. Maybe we can be more secure with computing, and it can go much faster. Next, please. Communications. Example.
Communications.
Yeah.
I'm not sure, like high-speed internet or something like that. I'm not sure.
Yeah, so it links nicely with quantum optics being applied for all this. So, communication currently, we use fiber optics, which means it is based on light traveling in fibers. Currently, in normal buildings and things like that, electrons moving. But now fiber optics is quite good. We make use of photons to transmit signals. And if we go further with the photons, we can fine-tune and get even better stuff in optical fibers. But even with optical fibers, a lot of quantum mechanics through quantum optics had to be applied. so that we will make those phone calls with our phones. Not in those days, remember? 1, 2, yeah. Those ones were based on wires, electrons. And now our communication, our cell phones, based on optical fibers, photons. And I will tell you towards the end today the reason or what quantum mechanics is about. It's a theory about largely photons and electrons and the materials in which these interact. Lasers, pretty obvious here. It's a quantum phenomenon to have lasers. And by the way, a reminder, what's the meaning of laser? That's where the quantum phenomenon shows up in the meaning. What's the meaning of laser? It's an acronym. Anybody, please? Go for it, you know. Light amplification by stimulated emission of radiation. That is a pure quantum phenomenon. Lasers are now ubiquitous, and people are beginning to use it both for good and a little bit for ill when they point lasers at Olympic or goalkeepers, to confuse them. Not good. Okay. But the good uses here are obvious. How about, we already dealt with quantum computing. So how do you feel now? Isn't it cool that you're going to get the theory behind all this good stuff? From getting healthy, medical, to defense, to communication. I mean, it's almost like there's nothing so cool that hasn't a quantum mechanical basis. So I'm excited to share the cool theory of quantum mechanics with you all this semester. Here is our daily schedule. So today, pre-test syllabus organization tests, the text we use. So text already. How many have this?
It's ordered.
It's very good. How many have the older one? It's okay to use the older one, but for problem solving, try to get this one. Is that okay? Since many of you have this new one, which is good, the problems are going to be based on this one. But if you have the older one, I'm okay with that because the changes are not so many. And if you couldn't get this, it's good to save some money because my slides will cover anything new here. And the homework, you can always check with others because I encourage you to work together for homework. Is that okay? So you can work with those who have this. I'm fine with you. If you have only the second edition, I'm fine with you reading that and working with those who have the third edition. So that's the schedule. How many of you have seen it on Blue Line already? Yes, you cannot do anything without Blue Line. So you need, for this course. It's where I update this. It's where you know what we are going to do and where you know the due dates. Even though I have it here for you, I can go ahead and share some documents so that things become clearer. That's the Blue Line I'm talking about. So what I'm going to hand over, I had already printed before I was told that the cost of printing has gone 4 times higher than last year, so we should print much less. The more reason, Blue Line. Yes. Okay, so I'm going to hand out so pick one and return the last. This will be your answer sheet for the pre-test. When we get there, you just do it. And while that is going on, I will hand out what follows, namely the actual pretest, and you will not write on the pretest. You will not write on the pretest. Just to take a copy, pass on. Okay. So now I hand out the syllabus. Like I said, I didn't, if I had the announcement that the cost of printing had gone 4 times higher, I wouldn't have printed. Now I wouldn't, but I had already printed, so go ahead and take a copy and pass on the rest, and I will pick extras at that point.
Can we get 2 more practice?
Sure. How many do you need, please? So we will do the pre-test towards the end, not now. Yeah, towards the end. It's just to make sure that you have everything that I printed. And next is, well, I had printed this as I did in the past, but now, henceforth, I will not be printing out so much.
Do you know why it went up so much?
Good question. We asked them. They said because they lost so much last year when there was not much.
Yes.
They are in debt. Yeah.
Makes sense.
And some of their suppliers, the cost of other things is such that if they don't increase, they will not be able to even continue. Yeah. All right. So you've got the schedule. You've got the syllabus, you've got the pre-test, and I think we can continue. We have spoken about the text, and we can then go to some more specifics. Please stop me anytime and ask questions. Today is lecture 0, meaning organization and you getting to understand what is expected. So, after class, I expect you to go to the blue line and check where things are. The detailed schedule, you have soft copy over there, as well as the syllabus. And next, so if, let's say, you are not able to make it to class for serious health reason, then you can join the class remotely, and we'll be able to accommodate you. We've done that in the past. So next, pre-test. So that's week 1, which is today, as a main thing that is due, and we'll get that done. What's due next week? Start of semester reflection. So all you need to do is click on it, on blue line, and you do the start of semester reflection. What else is due? Reading the text. So the preface and chapter 1, sections 1 to 3. And some of what I will say today, if we have the time, will actually help you get ready for that reading. And then there will be quiz 1 based on the reading. Yeah? So, and then homework 1 as well.
Is the homework due that day, or is that the day it comes out?
Yes, the homework is due that day.
Okay, so we'll get it after the first lecture.
I'm sorry?
We'll get the homework after the first lecture.
Yeah, the homework is already there.
Oh, okay.
I can tell you more about it. It's actually, I think the first 2-3 questions are on things you already know. It's a bit of statistics, connecting frequency tables with, and that's to prepare you for the statistical interpretation of quantum mechanics. Good question. Yeah. So I posted it last week. Yeah, I was really excited to get on this stuff. Any more questions? I really like questions because it helps me say what I want to say in a more, how should I put it, kind of natural way than pre-packaged. Yes, Millie?
Do we take the quiz in class or?
Good question. So the quiz is in class because Creighton wants us to do as much as possible in person. But it will be possible if something happens for you to take it remotely. But the quiz will be in class and paper-based. Yeah, any more questions? Answering the questions helps me say what's all the information better in my mind. So, yeah. So you got that I like holding office hours, but also I'm open to you coming in when my door is open. And I have some students who come in even when my door is closed. They just know, they just come right in. They just tap, and because it's not locked, they tap and come in. Yeah, they know I'm not going to send them away. And I like that because usually they really needed to see me. Yeah, and I like that. So stop by when you really need. Oh yeah, somebody here did that last week. Yeah, he just came. I had clothes I was walking, but he came in and it was fine. So that's good. So quiz is 10% of course grade. Homework 10%. Why do I keep it so low? I could make it 50, 40%, but why so low? Any idea? It's a lot homework, yeah. But the idea is to get you to really learn thoroughly through the textbook with each other and also with the resources available, how to do the problem, yeah, without too much pressure. And then the exams will test how you understood what you did, yeah, in the context. So that's the idea. So that it's not like, I have to get it. For example, if you get stuck in at a homework and it's almost time to submit, then you kind of acknowledge that you've given it a try. Your answer is not what is expected. If it was like a derivation or something like that, that's very reasonable and submit than spend 6 extra hours struggling because of the points you don't want to miss. Is that okay? And the grading will also take such good faith effort into consideration. It's not to mark you down, but to acknowledge the effort you have made. Because the idea is for you to learn something through it. And we test what you have learned through the 3 exams. So that's why each exam's 20%. Yeah. And there will be enough practice. And we'll be able to fix what was problematic for you during the homework. There is something in the syllabus which we will need to decide about homework. I may not follow the syllabus exactly, but yeah. So what is this quantum mechanics? I've already said a bit about it. It allows us to make sense of phenomena that we see at the level of electrons and photons. Can anybody guess what such phenomena were or are even now? What they were when they became a problem to the rest of physics, such that we needed quantum mechanics. Any guess from your modern physics? Photoelectric effect, ultraviolet catastrophe, yeah? So those are the things. We will touch them a little bit today. So some people think it is really tough, but the main challenge can sometimes be the fact that we need a lot of math to couple together the theoretical framework that allows us to explain this phenomena that we just mentioned and other phenomena. Photoelectric effect, absorption of radiation, emission of radiation, Compton scattering, and so on. Okay. Any question? All right. So there are famous quotations that kind of scare some people. Where Feynman, for example, remarked, "I think I can safely say that nobody understands quantum mechanics." What do you think about that? What do you think? That's already an introduction to the paradoxes. The theory explains experiment, but when you want to make more sense of the theory, it can be paradoxical. When you want to really grasp the theory in terms of all its non-experimental implications, it can be paradoxical. But as for your experiments, yeah, it has predictions that you actually measure and get results that prove the theory correct. So it is a theory that has experimental backing. But as for philosophical implications of the theory, some are paradoxical, even now. So there is room, there is work for you. It's not all complete to some extent. More practical things for our course, that's the grading, and what you will find. For graduates, that's what you get. For undergraduates, this course is open to both graduates and undergraduates. Okay? And what I have here is on the syllabus hard copy as well as soft copy. So do you think we should just kind of skip this and move forward since you have it online? Yeah? And you have hard copy. Is that okay? Can we go faster? So there are some legal notices, things about class cancellation, and there are lots of others in the syllabus. Yeah, disability, accommodation, and all that. So please make sure you go through it. There's something about the homework I thought we should think about before I speak briefly about myself. So I have it here. Each student will take impromptu turns in working out on the board some selected homework problems each week whenever homework is due. The idea is to get you to really know what you did and understand and be able to express to others. But there are also downsides here. Some people may really know what they did, but they are shy doing it on the board. And I don't want to put you on the spot. Does that make sense? So I acknowledge the challenges, so let's decide. You now see what I would love to do. Now let's decide what will work. And I'm not going to assume that what worked the last time I taught the course, which was just last year or previous times, is going to work for this group. Is that okay? So let's decide together. Another downside of this is, okay, homework 1 is due next Thursday, and I get to be picked, yeah? One of you gets picked to do it, yeah? So, and after that, since he knows that he has already been picked, he then relaxes the rest of the semester. Do you get what? While someone else who has not been picked is constantly under pressure. Not me, not me, not me. Until October or November. You get what I mean now? So that's not fair. Putting the last person who will get picked on the spot. I don't feel, although the aim is good, it may not achieve that aim so well. So what do you think? What should we do? I need your ideas. You know what I would like to see, but we've seen some of the shortcomings of that, so help me decide. Yes, please.
We could have multiple people do the same problem, like so that it doesn't have to be one person, and then we could more like at the end of the semester we could have more
Great
people.
idea. What do you think?
Yeah.
Which actually fits into group work, right? Okay, so let's make the groups now. Why not? Yeah. The first group, we could do 3, and then the last 2. Yeah. So 3, 3, 3. Who goes? Make your 3. Yeah, I can see. So there's 3. Which other 3?
We go down the line.
Okay, yeah. There's 3. 3, 3,
3. I'll be 3 with us go. Alright.
2.
and 2.
2.
Awesome. Wow. And then 3 there. Wow. So nice checking things with you. Better ideas coming, yeah? Multiple heads are better than one, right? Good, we've agreed. And so there will be not too much pressure. So legal notices, we have done that. A few of you know about me, and I usually don't like to surprise you. I want you to get from this slide the fact that I've been a student for nearly 3/4 of my life. So I know what you're going through. Is that okay? That's the reason. Yeah. I've studied different things, philosophy, physics, theology, yeah, in 4 different countries. And I guess what I can say is that it is sweet to be a learner. Yeah? Yes. And it is also sweet to have the opportunity to make use of what you learn. And Creighton gave me that opportunity, and see what I now share with you here in Creighton. Okay? So, and interestingly, Creighton is another wonderful place where research is done in order to help humanity. Service is very important. And guess what? I learn a lot from students. I mean, you guys, with all the things you have to do, so many of you are already volunteering in so many things. So many of you are working in addition and all that. And in many cases, you volunteer for things that help others tremendously. So service to humanity is taken very seriously by Creighton University. And I key into that, both in my research and my teaching, as well as in what I do after hours. So part of what I do is to get a hospital running 100% free of charge for the poor in my country of origin, Nigeria. It's running well. When I leave this class, I'm going to check what the matron did today. It's kind of cool. And I'm going to listen to some of the cool things you guys do. So it runs free, and we get a lot of support from my friends in addition to my salary that I send to get it free. All right, so about research, some of these are online, so you may be able to see it. Some of you are actually in my research group here. Yeah, I think there are up to 2 of you in my research group, so they can talk about more of that. Do what the slide tells you. And after that, I'll listen to some of you, to you all briefly. Oh yeah, I can. Yes, I can just pick. I can just share it.
You have a lot of people.
All right, so there you go. Okay. you. You love flying airplanes?
Yeah.
Wow. Okay. So we are going to do it. I do gliders.
Oh,
And the last time I did it was in the UK.
okay.
Yeah. So I need to get back to gliders.
Yeah, you should.
Yeah.
That's awesome.
She flies airplanes. I only manage gliders. You see?
Are you the Air Force? Are you Air Force Grace?
Thank you. So who else has something to share? I see somebody here who likes singing. That's cool, Millie. Yeah? Do we all have it here?
These are extra.
Okay, thank you so much. So anybody wishes to share something they like that they've written here? I'll be looking at it and making remarks as we go on. Is that okay? And you guys are already really looking familiar with yourself, so I like that. That's why you could form groups quickly, so no need going through this. Let's just continue to lectures to reason for quantum mechanics. What is quantum mechanics and why do we have it? Okay. So it is a theory that describes experiments, results about light and particles, especially electrons and protons. It may interest you to know that there are still some particles that quantum mechanics, as we have it, does not fully describe. Anybody give examples of such particles? That quantum mechanics, as we have it, does not fully describe. Unfortunately, yes, please.
There's some recent stuff about muons.
About
Muons.
muons, yeah. There are lots of subatomic particles that are only approximately described by quantum mechanics as we have it. So there's room for you to make new discoveries and come up with perhaps better theories. We don't even have a solid closed form equation of motion for the nucleus. It's an approximation using quantum mechanics. We have the Schrodinger equation, which describes behavior of electrons and can be extrapolated to the simplest of atoms, the one with one proton, one electron. After that, what is it? An approximation. But if it has already been used for so many applications. Imagine what would happen if we can have similar theory going down to so many subatomic particles, gluons, and things like that. So there's a lot left to be done. That's the idea I'm giving here. But what has been done so far is super cool. So why was it developed then? It turned out that there was a breakdown of classical mechanics when these phenomena were noticed for the first time. Around when was the electron discovered? At least confirmed to exist. Around 1900. That means 20th century, the first year in the 20th century by J.J. Thomson in Cavendish Laboratory. And I saw artifacts left behind by him because that's where I did my PhD. Now, when he did that, and so many other things followed, like photoelectric effect that could not be explained, it was clearly a breakdown of classical mechanics. What did we know by then? We were armed with the classical mechanics of Galileo, Newton. We had, for electromagnetic phenomena, Maxwell's equations and Faraday's discoveries. So we had the four so-called Maxwell's equations, none of which were by Maxwell, though, but he put them together nicely. But these could not explain the phenomena that we were seeing. And we've mentioned such phenomena already. Photoelectric effect, emission and absorption spectra by atoms, yeah, black body radiation. So we needed a new theory, and quantum mechanics was then developed. And it did explain many of those phenomena nicely, and it is a fundamental theory. It stands by itself distinct from this. So at this point, just to let you have a feel for what will be coming, it wouldn't be me lecturing from slides. I will be doing stuff on the board. So we are going to switch to the board and make the same introduction by writing some equations to back this up on the board as a preparation for what we will be doing, how the class will be going. And I will check the videos and see that things are working well, that you can see the board and things like that. So instead of continuing with the slides, good news. Whatever I'm going to have on the board, I usually have on the slides as well. But it is a pedagogical strategy to lay it out on the board. You see it unfolding and you can ask questions step by step than when I have everything on the slides. And you could just relax and follow what is happening on the board, knowing that in general, I also have it on the slides. But it is good practice to also so we'll do what works for you and let's see as it goes on. Is that okay? So, who changes the camera to the...
Doing a lot of exercise.
Excellent. So I can stop the slideshow. And leave it there. Then see where the camera is on panel 2. And change the lighting. Yes, so this should be better. And let's see. All right. Let's see how much I want to make use of. Nice. Okay. I can divide into 2. I may not pick all today. So YQN. Y was quantum mechanics developed. So you can now face the board, and it's important that we interact in class, not so much that we have a good video of it. We want to have both a good video of the interaction as well as the actual in here. So I'm more interested in you here because you've paid for it, right? Than the video of it. Okay, so stop me anytime to ask. And we mentioned the things that could not be explained using classical theories, which led to the need for quantum mechanics. And I'm going to use equations to then explain those things. For example, atomic emission, and absorption. Materials would emit and absorb radiation. And Planck had to make a hypothesis that the energy is not absorbed in a continuous way. That the energy must be absorbed in packets. The energy that is absorbed is quantized. So he made the hypothesis that you have done in modern physics, the Planck hypothesis, that energy, E oscillation, when you pick up an object, it absorbs and emits radiation. As you heat it up, it is getting, it's emitting. It's oscillating and emitting radiation. The sun, the energy, it's emitting radiation because of the heat. Thermal energy is getting off as radiation. If we pick up something and heat it up, it's getting energy, but it is emitting that energy as what? Radiation. How is it receiving that energy? It's oscillating, it's getting the energy, the thermal energy is becoming kinetic energy, causing oscillations of the atoms and causing emission of radiation. And he had to make a hypothesis that is different from classical mechanics to say that that energy is emitted in chunks of quanta. And it is given by that. And h bar is h over 2 pi. So h is Planck's constant. So basically, the energy of emission is proportional to the frequency. It's not continuous. It comes in chunks. So you can say Planck. See? So one reason. And you can also add black body radiation, but I don't want to write so much black body radiation. I want to focus on the equation. What other phenomenon did we say could not be explained by classical theories, please?
Ultraviolet catastrophe.
Sorry?
Ultraviolet catastrophe.
Yes, that's the one there, because that's the consequence. Yeah? Yeah. Yes, please.
Photoelectric effect.
Photoelectric effect, thank you. So, and Einstein then said, following Planck, Einstein made the same assumption that, see the step, Planck said energy is emitted in chunks. Einstein took it further and said, look, the photon itself that is getting into things and getting absorbed in what we are seeing in photoelectric effect, photon comes in, kicks out an electron. The photon itself is also not coming continuously as electromagnetic wave. The photon itself must be quantized. You see his additional idea there. For Planck, stuff, molecules are emitting radiation in chunks. Einstein took it further, that photons coming in to knock out electrons from objects, that the photons themselves are coming not as continuous waves as Maxwell's equation would predict, but they are coming out in chunks, in packets, such that we have one photon, one electron. And so that this energy, E photon, wow, that was a step further, that even radiation is quantized. That is Einstein. Proven by others, Millikan and so photoelectric effect. Another one. I didn't speak a lot about this, but this came more as confirmation of quantization. That, well, things, I mentioned it briefly, absorption, things like the nature of atomic spectra, things that Niels Bohr was handling to understand why is this color emitted and things like that. So he ended up accepting or proposing the same quantization in the behavior of atoms and molecules when he insisted that in his model, remember there were other models of the atoms, the ones that didn't work. Thomson's model was the pudding model, right? The Bohr model made a lot of sense because experiments could be explained using it. And here is what he assumed, the quantization of angular momentum. So n h bar. So this h bar is cool. Look, it means that h bar has the unit of angular momentum. Take note of that. And what's the unit of angular momentum? Of course, the unit of these two are joules, right? And electron volts, they are energy. Now we got angular momentum is quantized. Isn't that beginning to be sweet? Because these are conserved quantities in physics. Energy is quantized, angular momentum is quantized. Now you can predict. Make the prediction. What else must be quantized from conservation laws in physics? What else do you think must be quantized? You got energy quantized, you got angular momentum quantized, in chunks and packets. What else do you think you can project as possibly quantized? How about linear momentum? Yep, that's precisely the next reason we have quantum mechanics. Notice that so joules seconds, K is wave number. Look, all of them h bar, all of them a constant of proportionality related to the quantization. And to put this together, phenomena that are quantized could not be explained otherwise. You have to take the hypothesis that they are coming out not continuously, but in quantized fashion. momentum is quantized. This was just for completion, de Broglie, that even matter can have wave-like properties, yeah? And this was also made use of by Compton, yeah. So I'm connecting you clearly to a lot of phenomena, a lot of experimental results that depended on the idea of quantization, different from the predictions of classical or Newtonian mechanics and electromagnetic field. So it was clear at a point, reading all these and all these results coming out, and people successfully explaining phenomena by accepting or postulating quantization. Schrodinger said, surely, for all this to be put together, we need an equation of motion for these things. And he came up then with the Schrodinger equation, okay? What we now call the Schrodinger equation. So, an equation of motion for electrons to explain this behavior, yeah? Especially, for example, in the case of photoelectric effect. Well, if we get that, how the electron is able to get kicked out, yeah, using a particular equation of motion, then we can predict where it is going to go. If it gets there, yeah. If it lands in the next orbit, yeah, then the theory is proven. So we have 5a, the time-independent Schrodinger equation, to put all this together. So, and we will do a lot with it. I hit bar, partial, it's a time-dependent thing, of what he then calls the wave function for particles. Because all these phenomena had to do with particles behaving like waves and waves behaving like particles. So let's have an equation of motion for particles as though they were waves. A wave function should be a function for waves, right? But since electrons are behaving like waves and waves are behaving like particles, let's have a wave function for those particles, and in this case the electrons. So it said this must be equal to, yeah, so that allows us to, we can put the wave function there. It's a function of position in general and time, so I can add time, position and time. I can add the potential energy function, yeah, and of course itself again, the wave function. So that is the time-independent Schrodinger equation for a wave function, defined for a particle that behaves like waves. For example, electrons having wave-like properties, as in the de Broglie hypothesis, for instance, as in electron diffraction, for instance, again. Then, what we will be handling a lot in this course will be the time-dependent Schrodinger equation. Yeah? And it's easy to link it already. So, it will just be and this time, the wave function is just a function of position. Okay? The energy, yeah, and the wave function. So we'll be doing a lot with this. We'll use the wave equation. We will solve the wave equation for various potentials and see what it says about the energy levels of the particle that is behaving like the wave. In this case, electron bound to an atom, yeah. It should predict where it's going to be if we supply some energy. Yeah, it should predict its ground state and other energy levels in accord with these phenomena understood and explained well in terms of quantization. Yep. Makes sense? Where we're going, at least? Yeah. So you've heard about it, you're beginning to see it. So we wrap it up with the pre-test, and I hope that, yeah, your reading will already be something prepared for use in the class. When you're done with the pre-test, you can leave.